Okay, 8.3 is on polar form of complex numbers and de Moivre's theorem. We actually will have 5 different videos for this, and they're split up over 2 days. So today, 8.3 part 1 or day 1, there's 3 videos, so make sure you watch them all. And then you have day 2, there's 2 videos. Here are the learning targets. You can graph complex numbers. I can graph sets of complex numbers. I can find the modulus of complex numbers. We'll look at all of those today. I can write complex numbers in polar form. I can convert a number in polar form to complex form. I can multiply and divide complex numbers using de Moivre's theorem to find the power of a complex number, and then using de Moivre's theorem to find the roots of a complex number. But like I said, today we'll just look at graphing. In this video, we'll look at graphing complex numbers and sets of complex numbers and circles and different types of shapes. Okay, here's the complex plane. The complex plane, the horizontal axis is the real axis, and the vertical axis is the imaginary axis. You guys have plotted the complex plane before, where we have a complex number being a plus bi. So if we call z a plus bi, if that's the case, if z is equal to a plus bi, then z actually has a distance. If we take the absolute value of it, we have the distance using the Pythagorean theorem or the distance formula. So z would equal the square root of a squared plus b squared. It also is the same thing as our radius. So if you look here, the radius is equal to a squared plus b squared. You already know that in this, taking the square root of it. We also call that z, we call that the modulus. So the distance is called the modulus. So you can also see the modulus is also being the radius. So radius and modulus are about the same thing, but it's just on the complex plane. Instead of calling it the radius, we call it the modulus z. And it's found the same way. Use the Pythagorean theorem, a squared plus b squared, and then taking the square root of that. Again, remember that your horizontal axis, as you already know, is your real axis, and your vertical axis is your imaginary axis. All right, so the vertical is your imaginary, or the b part. Okay, so graph the complex number z and find its modulus. So keeping in mind, a is your real part. A is your real part. There's a, and b is your imaginary part. We plot it just like we've done before. So the ordered pair would be 4, comma, -2. So you can already see it's plotted. So write 4, 1, 2, 3, 4, and down 2, and we label it. All right, so 4 minus 2i. The modulus, remember that's the distance or the radius, would be, using the Pythagorean theorem, we'd say 4 squared, actually the square root of 4 squared plus -2 squared, which is 16 plus 4 square root of that equals the square root of 20. Simplify that to be the square root of 4, square root of 5, which is 2 root 5. So it's said that the modulus of 4 minus 2i is 2 root 5. 5i, you guys can also see that as 0 plus 5i. So the real part is 0 and the imaginary part is 5. How do we graph it? It's nowhere left or right, and then up 5. 1, 2, 3, 4, 5. And that distance, we could use the Pythagorean theorem, to find the distance, but we don't need it because there's no horizontal change. The vertical change is just 5, so the modulus is 5. -3, you can see that in the complex form as 0 plus, or -3 plus 0i. There's no vertical change, but to the left, we move 3, 1, 2, 3. It's easy to find that modulus is 3. Okay, graph the complex number z and then sketch 2z, 1/2 z, and its conjugate. So if we have z equals 2 plus 2i, we can see that 2 times z, and you can see they're already done here. 2 times z is just distribute the 2 to the 2 plus 2i, and you get 4 plus 4i. 1/2 z is multiply the 1/2 times the 2 plus 2i, and you get 1 plus i. And then the conjugate, you guys remember when we used to multiply denominators, we didn't like roots in the denominator of a fraction. We'd multiply by the conjugate. The conjugate of 2 plus 2i is 2 minus 2i. That is just the conjugate of 2 plus 2i. Now graphing these, the first one would just be 2 comma 2. So you can see right 2, up 2. You can see it's right there, 2 plus 2i. 2z is right 4, up 4. So 1, 2, 3, 4, up 1, 2, 3, 4. Label it. 1/2 z is right 1, up 1. Right 1, up 1, and label it. And the conjugate, right 2, 1, 2, and down 2, and then label it. No big deal. Okay, now this is graphing the set in a complex plane. One thing you have to be aware of is that z equals a plus bi. A is your x, and then b again is your y. So in this case, this is saying that x is positive, and y, b being your y is negative. So what quadrant does that put you in? It puts you in the fourth quadrant. So 1, 2, 3, 4, put you in the fourth quadrant. All right, and then it's everything in that quadrant. All right, so it's everything a is greater than 0, greater than or equal to 0, and b is less than or equal to 0. So everything in that quadrant is good, and that's why it's all colored in. Solid there because of the equals. But again, everything greater and less than would be everything in that entire box, in that quadrant. Okay. The next one. All right. It says z, remember what z is, that represents the modulus. Absolute value of z equals 4. So I want you to think about that one. 4 is like your radius. And so if you think about it, the radius of 4 in every direction, that's every direction, everywhere, would give you a circle. So graphing that modulus, absolute value of z, gives you a circle. It's just a circle. Okay. That's a modulus, distance. All right, here it is where absolute value of z is only greater than 3. So I want you to think about that. If it's greater than 3, well, the radius is 3 in every direction. 1, 2, 3, 1, 2, 3, 1, 2, 3. It's dotted. It's dotted because it's only, let me show you that. It's dotted only because it's greater than. If it's greater than or equal to, like the last one, it would be solid. In this case, it's just equal. All right, but it's also greater than. So what does that mean? Well, we would shade everywhere greater than the circle, which is everywhere there. All right. Another one, a linear graph. All right, a plus b is less than 1 is the same thing as x plus y is less than 1. If you wanted to solve that, x plus y less than 1 would be y is less than negative x plus 1. Just subtract x on both sides. And then you graph it. I get the dotted line. You guys all know how to graph linear equations. The y-intercept is 1, and then up 1, right 1, up 1, right 1, make a straight line. And the line is dotted because it's only less than. And then, of course, you guys all know it's an inequality, so shade below, just like so. Okay, that concludes just graphing lines and graphing graphing points and graphing a set of points. Make sure you watch videos 2 and 3.